Jai Hind everyone. So this is our second lecture and its topic is number system arithmetic and Hamming code. So in number system arithmetic we will be first covering the binary addition. So these are the rules for binary addition, which can be summarized in form of two variables are there, a and b are there, and we will be computing the sum and carry for that. So if we look at this thing here, if these two variables 0 and 0 are added, I am getting the sum as 0 and carry is also 0. And if 0 plus 1 is added, sum is 1, which is represented by 0 1 in binary. Similarly, this is also 0 1, then 1 plus 1 is 2 in decimal, and in binary it can be written as 1 0. And then triple 1 is 3 in decimal and 1 1 in binary. And similarly, if I repeat this and split the sum into two parts, sum and carry, then it can be seen that 0 plus 0 is sum 0, carry 0, and 0 1 sum is 1, carry is 0, then 1 0 sum is 1, carry is 0, and 1 plus 1 sum is 0, carry is 1, and triple 1 sum is 1 and carry is 1. And now using these rules we can add these two numbers. Now A is mentioned here, B is mentioned here, and we are computing the sum. 0 plus 1, 0 plus 1 is 1 with carry 0. And similarly 0 plus 1 plus 1 sum is 0 and carry here is 1. Then 1 plus 0 plus 1 is your sum 0 and carry 1. Then 1 plus 1 plus 0 again sum 0, carry 1. Triple 1 1, carry 1. 1 plus 1 0, carry 1. So here A and B are not there, so I am adding two zeros here. So 1 plus 0 plus 0 becomes 1. So this is my final sum, and so that's it. This is about the binary addition. Now coming to the representation of the negative numbers, it can be represented in three forms: sign magnitude representation, ones complement representation, and twos complement representation. So sign system is pretty simple one. We are just adding a additional bit, and that will be signifying that my number is positive or negative. And similarly, if I am using ones complement, it has an advantage that I can replace subtraction with addition if I use ones complement to represent negative numbers, and it can be derived simply by replacing 1 by 0 and 0 by 1. Similarly, 2's complement has an advantage of replacing subtraction by addition, and it is obtained by adding 1 to the 1's complement. So let's check this in the next. So I am taking a number 7. 7 in binary is represented by triple 1. So in sign magnitude system, we can see that it is here an extra 0 is added. That 0 is signifying my number is positive. And similarly here, for minus 7 I am adding an extra 1 here. It is signifying that my answer is negative. Okay, so this is simple sign number representation. And now coming to the ones complement system. In ones complement system, this 7 when written in binary is 0 triple 1 is represented in ones complement form by just flipping the bits. So that means 0 is replaced by 1 and 1 is replaced by 0. So the number becomes 1 triple 0. So this is my ones complement. And similarly now going to the twos complement. So for twos complement, I am using this ones complement here and then adding 1 to it to get my twos complement. So it becomes 1001. But there is a shortcut for computation of twos complement. If let's take an example for this. Now let's suppose I am having a number 1010.10. So if I want to compute twos complement of this number, okay, so it's twos complement. For twos complement, I will start looking from the extreme right. I will retain all the zeros and first one. So if there would have been more zeros, I would have retained them. So I have retained all the zeros and first one, and then coming to the next part and flipping all the remaining bits. So 0 will be replaced by 1, 1 will be replaced by 0. Similarly, this 0 by 1 and this 1 by 0. So this becomes my twos complement. So in this way, this is my shortcut for twos complement. So now let's proceed to the different representation of these numbers in signed 1s and 2s complement form. So this 0 to 15 is actually written in decimal only, but when we are using signed magnitude representation, if there is if we consider that all the numbers are positive, then this 0 to 15 will be used for 0 to 15 positive numbers. But to represent negative numbers, these 8 zeros are denoting my positive number, and these 8 ones are denoting my negative numbers. That means these are negative numbers and these are positive numbers. So in sign magnitude representation, these 0 to 7 are for plus 0 to 7, and here these are minus 0 to 7. And similarly in ones complement form, if we see, then these positive numbers are identical in sign in ones and twos. That means positive numbers remains unaffected by the sign representation, ones complement representation and twos complement representation, but these negative numbers all are having different values in all three different systems. So if we check the range of these, so if we are interested in finding the range, so for signed I can easily see that range is minus 7 to 7. Similarly for ones complement, I can see that range is same, minus 7 to plus 7. And for twos complement, here I can see that there is a minus 8 here. This minus 8 has been possible because there is no negative 0 here. In sign and in ones, I was having a minus 0, which is quite ambiguous because minus 0 has no meaning. Okay, so this minus 0 is being replaced by minus 8 in twos complement. That is an advantage of twos complement as well. So we can say that range of twos complement is minus 8 to plus 7. So it has an extra value. There is an extra value in twos complement. So now coming to the subtraction using these complements and the direct subtraction method. And for direct subtraction, we will be using these rules. If I subtract a minus b, then difference will be 0, borrow will be 0. If I subtract 0 minus 1, then 0 minus 1, difference will be 1, borrow will be 1. If I subtract 0 from 1, that means 1 minus 0, then difference will be 1, borrow will be 0. And similarly 1 minus 1 will be difference 0, borrow 0. Here the only case which needs an explanation is this one, 0 minus 1. So 0 minus 1, if I am doing this, actually I am subtracting a larger number from a smaller number. So in that case, this is not possible, so I will be taking a borrow from this. That means this borrow is guaranteed. Now if I take a borrow here, now this becomes 1 0. Now this 1 0 is equivalent to 2. If I subtract 2 minus 1, then it will become 1. So that's why difference is also 1 and borrow is also 1. Now we can use these rules to perform subtraction. So if I am interested in doing this, I have mentioned a question here. This 1100 is actually your 12, and this 1001 is actually your 9. So I am subtracting 9 from 12. So I should be getting plus 3. Let's check this whether we are getting this or not. So 1100 minus this 1001. So if I am doing this, so 0 minus 1, from the above table we can see that 0 minus 1 is difference 1 and borrow 1. So borrow, that means I have to subtract. I have taken borrow from here, that means there is a negative here. There is a deficiency of minus 1 in the next three. So again 0 minus 1, it again becomes difference 1 and borrow 1. Now 1 minus 0 minus 1, effectively it becomes 1 minus 1, that means it becomes 0. Similarly and there is no borrow, so I am mentioning a minus 0. I have not taken borrow from this case, so I can put a minus 0 there. So 1 minus 0, it again becomes 0. So 0 0 1 1. So if I convert this into decimal, it will become 3. So which is absolutely correct. So in this way we can perform direct subtraction. Now coming to the ones complement subtraction. For this, if I want to subtract y from x, then y is my negative number, so the negative number has to be complemented. So I will once complement this number y and then add this to x and then check whether there is carry or not. If there is carry, then my answer is positive, and if carry is not generated, then my answer will be negative. Okay, so but in both the cases, in first case when the answer is positive, when carry is generated, I am mentioning that the answer is positive, but it is not the answer, and to finally get the answer I have to add this carry back to the addition result. And similarly for this subtraction part, sorry, this not carry generated part, in that case I have to again take 1's complement of the addition result to verify my answer. So okay, so we can, so now let's perform these questions using this 1's complement method. So if I need to subtract this 25, that means 15 from 25. Okay, so this 25 can be written in binary as 1 1 0 0 1, and this 15 can be written as 0 1 1 1 1. And if I had to perform this subtraction for this, then this number has to be 1's complement. So if I find the 1's complement of this number, then I can see that it will be 1 0 0 0 and 0, and this number will be copied as it is 1 1 0 0 1. So, and if I add these numbers, so 1 plus 0 will become 1, then 0 plus 0 is 0, 0 plus 0 is 0, then 1 plus 0 is 1, and then 1 1 is 0, carry 1. So there is a carry here. So this carry indicates that my answer will be positive. Okay, but to get the answer I have to add this carry back to the sum. That means this thing. So 1 plus 1 will be 0 and carry will be there. So 1 plus 0 1, similarly 0 1 0. So I am getting this. That means plus 10. This is what I am getting here. Which is the correct answer, because 25 minus 15 in decimal is equivalent to your 10. Similarly, if I perform this 15 minus 25, so 15 is your 0 1 1 1 1, and this 25 is your 1 0 1 1 0 0 1. Here this 25 is negative number, so this 25 will be 1's complement. So if I perform the 1's complement of it, then it will become 0 0 1 1 0, and I will retain this number as it is 0 1 1 1 1. And if I perform the addition of these two now, 1 plus 0 is 1, then 1 plus 1 is 0, carry 1. Now triple 1 is 1, carry 1, 1 plus 1 is 0, carry 1. So 1 plus 0 is your 1. Now there is no carry. Carry is not generated. That means my answer is negative. And to get the answer as per the rules, I have to again take the 1's complement of this number. So if I again take 1's complement, then it will become 0 1 0 1 0 with a negative sign. So I can easily see that the answer is same, but this time it is negative. That means it is minus 10, which is absolutely correct, because 15 minus 25 is actually equivalent to your minus 10. Okay, so this same thing can be done with the help of 2's complement as well. So this 2's complement is actually adding 1's complement and 1. But we will be using the shortcut. The rules are exactly the same except for this 3a part. So if the carry will be generated, then I will discard the carry. That's the only difference between the rules for 1's complement and 2's complement. Rest all the rules are same. So if we again check these questions again with the help of 2's complement now. So 25 is now my again 1 1 0 0 1 minus this 15, that means 0 1 1 1 1. So now this has to be done using 2's complement. Now I will be finding the 2's complement of this number. So 2's complement of this number can be found by using the shortcut, looking from the extreme right, retaining all the zeros, but zeros are not there. So I have retained the first one and now complementing the rest of the number. So this is the 2's complement, and this number is positive, so it will be retained as it is. Now if I add these two numbers, 1 plus 1 is 0, and then there is a carry 1. 1 plus 0 plus 0, 1 plus 0 plus 0 is 1, and then there is carry 0. Triple 0 is 0. Now 1 plus 0 is 1, and 1 plus 1 is 0 with carry 1. So now this 1 indicates that my answer is positive, and in 2's complement we have an added advantage that we do not have to do anything now. We just have to discard this carry. This carry is to be discarded only, and the remaining part is my answer. That means it is plus 10. Okay. Now similar thing can be done for 15 minus 25. So this 15 is 0, 1, 1, 1 and 1, and 25 is 1, 1, 0, 0, 1. So now this time 25 is negative, so it will be 2's complementary. So finding the 2's complement of this, retaining the first one and complementing the rest of the number 1, 1, 0, 0, and retaining the first number 0, 1, 1, 1, 1, and now adding these two numbers. So 1 plus 1 is 0, carry 1, triple 1 is 1, carry 1, again triple 1 is 1, carry 1, and 1 plus 1 is 0, carry 1, and 1 plus 0 is 1. So there is no carry. This number was in 5 bits, this number is also in 5 bits, and the sum is also in 5 bits. So there is no carry. So there is no carry, that means my answer is negative. And to get the answer, I have to again take 2's complement of this number. So if I again take 2's complement of this number, then again using the shortcut, retaining all the zeros from the right side. So there is only 1 0, and retaining the first one and complementing the rest of the number. So this 0, 1, 0 with a negative sign. So this is same as the answer in previous case, but this time with a negative sign. That means it is minus 10. So this is my 2's complement subtraction. Okay. So now we will be going to the next topic, which is Hamming code, error detection and correction. Clear? So this is very important topic. In the last few years, this has been a common question in all those exams. In the last 3-4 years, I think there has been no question paper in which this question is not there. So it is very important. So this Hamming code is used for error detection and correction purpose. It uses the concept of additional parity bits. That means if we are having a message which is having some bits, then using this Hamming code we have to add some extra parity bits in it to prepare the Hamming code. So, and this parity, a term is mentioned here, that this parity. What is this parity? Parity means the number of ones. Number of ones in a message. If it is even, then it will be considered as even parity. And similarly, if it is odd, then it will be considered as odd parity. That means if I look at this message, I can count the number of ones in this message. So there are 4 ones. So I can say that this message has even parity. Okay. So this is the parity bits. So let's understand this Hamming code by an example. We have to prepare Hamming code for this message. So first thing is to check the message bits. So if I count the number of bits, I can easily see that there are 7 bits. Okay. So now using this Hamming code concept, we have to add some extra bits. And what is the formula for adding these bits? This is the formula. And if I put m is equal to 7 in this, so this formula reduces to this, and I have to find the minimum value of p for which this relation is satisfied. So if I start putting from 0, 1, 2, 3, I can easily see that this relation is satisfied for p is equal to 4. So p is equal to 0, 1, 2 and 3. For these 4 values, this relation is not satisfied, so I am getting this value p is equal to 4. So the total number of bits become m plus p. 7 were the message bits, 4 are the parity bits, so m plus p becomes 11. So now we can prepare the Hamming code, but before going to the Hamming code structure, we have to first identify where these bits are to be included. So this step 2 is telling us about the location of parity bits. So these are the 4 bits which are to be included in my message. So 1, 2, 4 and 8. That means 2 raised to power 0, 2 raised to power 1, 2 raised to power 2 and 2 raised to power 3. These are the 4 locations where these 4 parity bits would be added. So if there would have been an extra bit in some other example, if there would have been 5 parity bits, so 16 would have been location for that 5th parity bit. So the structure of Hamming code becomes, there is a parity bit at 1st position, 2nd position, 4th position and 8th position, and for the rest of the positions the number is copied, which we can see in the previous slide that it was 1101001. So we have copied this number. So this becomes the structure of Hamming code. So now coming to the last step, finding the value of these parity bits. Now if these values are known, then I can finally prepare my Hamming code. So regarding the finding of these values, we have to write the binary version of this 1 to 11, because we are having these 11 values here. So for this 1 to 11, I am writing the binary representation of them. And for this LSB, I will be using P1. For this position, I will be using P2, then P3, and then P4. So if I check the column for P1, I can see that there are ones at 6 positions: first position, third position, fifth position, seventh position, ninth position, and 11. 1, 3, this is 1, this is 3, this is 5, this is 7, this is 9, and this is 11. Similarly for P2, there are ones at 2, 3, 6, 7, 10, and 11. Similarly for P3, there are ones at 4, 5, 6, and 7. Similarly for P4, 8, 9, 10, 11. So I have mentioned the bit combinations here. So using these bit combinations, I can find the value of these parity bits. So P1, for finding the value of this P1. Now I have to go back to the question. There would have been mentioned that prepare Hamming code using even parity. So if examiner has mentioned that prepare Hamming code using even parity, okay, examiner can also ask to prepare this code using odd parity. Okay, so now we are considering the Hamming code preparation using even parity. So at first position there is P1, and third position there is a 1, and fifth position there is a 1, seventh position there is a 1, ninth position there is a 0, 11th position there is a 1. So if I calculate the number of ones, there are 4 ones there. 4 is already even. So if it is already even, then P1 should be 0, because if I put P1 is equal to 1, then number of ones will become 5 and it will become odd. But the examiner has mentioned that prepare Hamming code using even parity. So I am putting this P1 as 0. Similarly, now we can compute the value of P2. So P2 for this second position is having this P2. Now third position is having a 1, and then sixth position is having a 0, seventh position is having a 1, and then 10th position is having a 0, 11th position is having a 1. So if we calculate the number of ones in this message, there are 3 ones. That means it is odd. So to make the resultant parity even, that P2 has to be 1, so that total becomes 4 and it becomes even. So I have put here P2 is equal to 1. Similarly, I can calculate the value of P3 and P4, which are coming out to be 0 and 1. Now I have calculated the values of P1, P2, P3, and P4, and if I replace these values here, so the structure for Hamming code will become like 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1. So this is my Hamming code. So if we are asked to prepare this Hamming code using odd parity, we can also do this. In that case, these values would have been complementary. So 0, 1, 0, 1 would have been 1, 0, 1, 0, and the Hamming code would have been slightly different in that case. So this is the computation of Hamming code using even parity. Now it was also mentioned that we can detect and correct the errors using Hamming code. So to understand that part, now let's suppose the received code is this one. I have introduced an error. The code which I have prepared in the previous slide, I have introduced an error in this, and the receiver has received this code and it has to judge on its own that whether there is any error or not. And if there is any error, then it has to correct it on its own. The only thing which receiver is aware that is this thing, that this code is being prepared using even parity. Okay, so using this, the receiver has arranged these 11 received bits in this format, and then using these same bit combinations which were being used at the transmitter 1, 3, 5, 7, 9, 11. So if I check this position 1, 3, 5, 7, 9, and 11, I can see that the number of ones at these 6 positions, total number of ones here are 3. 3 is odd. Okay, 3 is odd. So there is a conflict, because while preparing this code, I had ensured that the parity should be even, but now I am getting the odd parity. That means there is a conflict here. So I am mentioning why. That means yes, there is a conflict, and I am denoting this yes by 1. Okay. Similarly for this P2, 2, 3, 6, 7, 10, 11. So if I check these combinations 2, 3, 6, 7, 10 and 11, I can see that again there are 3 ones. 3 again it is odd, so there is a conflict, denoting this conflict by 1. And now proceeding to P3, if I check these 4, 5, 6, 7, this 4, 5, 6 and 7, if these 4 bit positions are checked, there is a single one, there is only a single one, and that means 1 is odd. Again there is a conflict, so again denoting this conflict by 1. And now proceeding to the last bit combination 8, 9, 10 and 11. In 8, 9, 10 and 11 I can see that there are 2 ones here, 2 ones, that means it is even, that means there is no conflict, and this no conflict is denoted by this 0. And now arranging these conflicts, no and yes, and replacing yes by 1, no by 0 in reverse order, I am getting 0, 1, 1, 1. So this 0, 1, 1, 1 in decimal is equivalent to 7. That means there is error in 7th position. So if there is even a single conflict, if there is even a single conflict, then I can ensure that there is an error. And to find the error, I have to replace these yes and no by 0 and 1. So in that case, I can see that my error is in 7th position. So if I replace this 0 by 1, I can get my corrected code. So if I replace this 0 by 1, then this becomes my corrected code. So I have written it here that this is my corrected code. So in this way, Hamming code has been used to detect the errors first, and then it has corrected the errors. So if the examiner has mentioned to perform this using odd parity, this can also be done. In that case, there would have been same bit combinations would have been checked, and conflict would have been mentioned if the resultant parity would have been even. In that case, conflict is generated when the resultant parity is odd, because the code was prepared using even parity. Okay, so the conflicts have to be replaced by 1 and non-conflicts are replaced by zeros. So in this way, we can prepare, detect and correct errors using Hamming code. So you can take this question as an assignment and perform the same thing using odd parity. Okay, so this is about the today's lecture. Thank you very much.